Welcome back to our third lecture. Today we're gonna finish this chapter about quantum measurements first, and then we go into composite quantum systems, which then will lead us to entanglement. And I think on Thursday we then gonna close this chapter after discussing Bell's inequality. So let's now continue with quantum measurements. And first, let me do a short recap of what we've learned last time. So last time we stated our postulate 3, which was about quantum measurements. And there we said that quantum measurements are described by a set of operators which satisfy the completeness equation. So sum over m, dagger, m equals 1. And the probability to get the outcome m. So the indices they correspond to the different outcomes of the measurement. And the probability to get the outcome m was given by the trace of m dagger, rho. And our state after the measurement, the so-called post-measurement state, is given by m rho, dagger, divided by P of m, which is trace of m dagger, Okay. So first thing that I'd like to recall here in particular is, the reason that we have this completeness equation is the fact that the probabilities must sum to 1. Okay. So this is what we calculated the last time. And the next thing is the post-measurement state here. So the fact that we divide by this probability P of m is because the state after the measurement must fulfill our characterization requirements for a density operator. One of them is that the state must have trace 1. Okay? If you perform the trace of the state, you see that this has trace 1, right? Because that's the reason why we divide here by this factor. And you might also wonder, why did we actually have these requirements for these density operators that we stated? So we said that the density operator must have trace 1 and it must be positive. Okay? The fact that it has trace 1 is again the fact that probabilities must be conserved. So the diagonals of our density operator is nothing else than a probability distribution, right? And if I sum all probabilities, they must sum to 1. And this is why density operators must have trace 1. And the next thing is, why must the density operator be positive? The reason is actually this one here. The reason is that the probabilities cannot be negative, right? So this m dagger m, this one here is positive. It's a positive operator. And in order for these probabilities to be positive, rho must also be positive, right? Again, you can think of this density operator on its diagonal in the matrix representation. On its diagonal, there's a probability distribution, and these probabilities must be positive. And that's why a density operator must be a positive operator. Okay. Let's briefly state the fact that this m dagger m is positive, because we're going to use this just in a second. So m dagger is positive since for all elements of our Hilbert space we have that we m dagger we is nothing else but the norm of v squared, and the norm is always positive, right? And hence this dagger is a positive operator. I just want you to see this, right? Okay, and now with this postulate that gave us these characteristics here, we can now take a look at some specific measurements. Okay? The first one that I'd like to discuss is the one which you probably already have heard about is the so-called projective measurement. So this leads us now to a chapter 1.3.2.1. So what is a projective measurement? Projective measurement, so it's often also called a projective valued measure. Yeah, valued measure. Or sometimes also called von Neumann measurement. This is described by a Hermitian operator. Say, let's call it M on our Hilbert space, which has the spectral decomposition M is equal to sum over all outcomes M, then the eigenvalues M in our projectors M on the subspaces. So this is equation 135. So here these projectors PM, they project onto the eigenspace with eigenvalue M. They constitute the measurement operators of the measurement. So these projectors onto the eigenspaces correspond now to our measurement operators. Okay. So this is actually a specific case of our postulate from the quantum measurement. It's a very particular measurement where our measurement operators satisfy, so the measurement operators are projectors, and the projectors, so recall that the projectors satisfy PM, PM prime, DM, M prime, PM. Okay, so they're orthogonal, and if I square them, I get the projector back. Okay, the outcome, okay, we can now simply plug this in here, what we know from the postulate. So the outcome is now the probability to get the outcome M is simply trace of PM rho, and the post-measurement state is PM rho PM divided by this probability. Okay. And as an example, consider now an observable. So we call this Hermitian operator an observable usually. Okay, I didn't. So this Hermitian operator is usually called an observable. I didn't state it here explicitly, but I guess you heard it several times already. So as an observable, now consider sigma z, so the Pauli z operator, which is 0, 0, minus 1, 1. So we have two outcomes. M equals plus 1, okay, and M equals minus 1. The projector into the eigenspace with eigenvalue plus 1 is 0, 0, and the projector onto the eigenspace with eigenvalue minus 1 is 1, 1. So you have the measurement operators. Zero, 0, 1, 1. And this is exactly the example that we considered last time. If you remember, last time we considered an example of a two-level system and considered a measurement with these measurement operators. And the example that we did was indeed a projective measurement. So I'm not going to go further here. You can take a look at the example that we did last time. So let's now come back to this postulate. If we perform an experiment, it happens very often that the post-measurement state is not of interest. Okay? The reason is, for example, consider you're doing an experiment with photons and then you measure a photon, and usually by such a measurement you destroy the photon. So you absorb it and then you get a signal. Or say that you do a measurement, and after this measurement, you can conclude what the measurement. So meaning that the post-measurement state is not of interest. And this happens very often. And if this is the case, we can use the very rich formalism and very useful formalism of so-called positive operator valued measures. Okay? We're going to use positive operated value measures several times. And this is very useful formalism. You will see it in a second. Why it is so useful, because we can compress our notation a bit. So this brings me now to chapter 1.3.2.2, POVM measurements. So if the post-measurement state is not of interest, we can use the formalism of so-called positive operator valued measures. So in short, it's POVM. So to this end, let us define the operators EM equal to now this M dagger MM. Okay, we've just seen that they are positive, and that's where the name comes from. These EM operators are positive operators, and what they satisfy is that if I sum over these operators, I get the identity. Okay? This is simply nothing else than restating the completeness equation. So you see that simply with this definition of a positive operator, we could now compress the formalism because we don't have these daggers anymore, but instead we have a single positive operator. And the reason is if we forget about this post-measurement state, then we are only interested in the probability, and there we see, okay, there's only dagger appearing, right? Well, if we would have to consider the post-measurement state, we could not do this compressing of our notation, because there we have m on the left side and dagger on the right side. Okay, so we would not be able to compress them to a single operator. So with this, we can now define a POVM. A POVM is a set of positive operators satisfying sum of m, em. So a set of positive operators em satisfying this completeness equation. Well, that's it. This is a POVM, right? So let's do some remarks. The first thing is, you can now wonder, well, given any such set of positive operators which satisfy this equation, can I find actually a measurement? So can I find these measurement operators which realize this POVM? And the answer is yes, you can. So meaning that for every POVM, there exists a measurement, or there exists a set of measurement operators. And the proof is fairly simple. So to prove this, let us define the measurement operator as the square root of em. Okay, this is the positive square root. We have a positive operator, em, so we can take the square root. And we're taking the positive square root. What then happens is that m dagger is also the square root of em. Okay? And if we sum over this is nothing else than summing over our POVM elements, gives the identity. And this is all that is required. Okay? And I think I forgot to mention that these positive operators, em, we call them sometimes the POVM elements. Okay, so these are called POVM elements. So these measurement operators here, m, and these e's are the POVM elements. Okay, so let me continue here with our second remark, is that projective measurements are POVM measurements with the POVM elements being projectors. So this is fairly easy to see. And as a last remark, POVM measurements are the most general kind of measurements that you can think of in quantum mechanics. So there's one more theorem that I'd like to briefly mention, because we're going to use it at some point. It's the so-called Neumark theorem. And it relates now POVM measurement with projective measurements. So it's theorem 1.7. And Neumark theorem says that any POVM can be realized by extending the Hilbert space to a larger space and performing a projective measurement. So it says that we take our Hilbert space, which describes our quantum system. We enlarge the space, so we say there's a bit more, okay, there's more, we enlarge the space, and then on this larger space we perform a projective measurement, and this projective measurement, it performs a POVM measurement on our Hilbert space of our system, okay? And unfortunately at this moment we cannot prove it. The reason is that so far we didn't discuss composite systems. Right? So we don't know how to enlarge our space. So this is exactly what we're going to discuss in a second. So the proof is going to be an exercise for you once we discussed composite systems. Okay? And this is a fairly simple proof, and possibly at some point at the end of the lecture when we discuss quantum information theory, then we're going to prove this later on, okay? But the reason that I stated here without proving and without actually being able to prove it is because we're going to use this. We need this theorem, okay? So the proof, you can easily do the proof by your own once we discuss composite systems. So this brings me now to composite systems. So suppose now that we have not only a single quantum system, but more than one quantum system. For example, you can think of there's a two-level system, there's a two-level system. Now we're going to ask, how do we describe the joint system of these two single quantum systems? Okay, we call then this a composite system, and this is now described by our last postulate, which is postulate 4. So it says that the state space H of a composite quantum system is the tensor product H1 tensor H2 and on to Hn of the Hilbert spaces Hj of the components, so of the component physical systems and now if system J is separately prepared in state rho J, then the joint, the state of the joint physical system is the tensor product rho 1 to rho 2 rho n. This is our last postulate. And let me stress that this is the state if I do prepare these individual states separately. Okay, so there are no correlations. Then we write this as such a tensor product. But so far we don't actually know what the tensor product is, right? So we didn't define the tensor product. So let me define the tensor product. So the function from H1, so it takes an element of H1 and H2 and maps it to H1 tensor H2. It maps it maps an element V of H1 and an element W of H2 to as how SVW is mapped to VW, where the dimensions of H1 tensor H2 is the product of the dimension of H1 times the dimension of H2. Okay, so please note that this is not the inner product here. It simply says that this is a tuple of two states. So this tuple is mapped to the tensor product. And so far we simply stated, okay, that the dimension of them is the product of the individual dimensions. And now let us define the properties here. So for all V, V1, V2 in H1 and W, W1, W2 in H2 and set in Z in complex numbers. It satisfies the properties that I'm going to write down in a second after I cleaned the board. So the first property is that if I have this complex number Z and our tensor product VW, then this is equal to ZV tensor W, which is equal to V tensor ZW. And we simply write this as Z V tensor W. It's equation 1.33a. Then the second property is that V1 plus V2 tensor W is equal to V1 tensor W plus V2 tensor W. And the same property for the second space, so it would then be V tensor W1 plus W2 is equal to V tensor W1 plus V tensor W2. So now we, so to say, defined how we calculate the tensor product between two state vectors. The next thing is, how do we now calculate if an operator acts on a state? So this gives us definition 1.14. So we have for linear operators A on H1 and B on H2. We have that A tensor B acting on state Aj, Vj tensor Wj is equal to sum over J Aj A Vj tensor Bwj. It's equation 1.37, where these Aj's are complex numbers and Vj's are in H1 and Wj's in H2. So with this, we now know how an operator which lives in the composite system acts on the state of this composite system. Okay? So it's simply performing this operation component-wise here. And then the next thing that we need is how do we perform the inner product now on this composite system. So it's definition 1.15. So how do we define it? Say we have some composite vector Vj tensor Wj. Okay, now this is the inner product with bk, and then we say, let me call this v prime k tensor w prime k. So I'd like to do this now step by step, actually. First thing is we use the linearity of the inner product. So this is nothing new. The next line is nothing new. So we can write this as sum over j and k, and then a complex conjugated j, bk, and then the inner product of vj tensor wj with v prime k tensor w prime k. So this is nothing new. This we already know from the properties of our inner product. So it's linear in the second component and it's conjugate linear in the first component, meaning that the a's become complex conjugated, okay? Because it's conjugate linear in the first component. But now, how do we calculate this inner product of our tensor products? It's simply the inner product in our first space multiplied by the inner product of the second space. So it gives sum over jk, aj star, bk, and then the inner product of vj with vk prime times the inner product of wj with wk prime. So this is for all aj, bk complex numbers, then vj So the inner product is simply the inner product in the first space times the inner product in the second space. That's how we define it. So let me now state a few remarks. The first one is about the dimensions. Okay, so we've seen that if the dimension of the first Hilbert space, say, is D1, and the dimension of the second Hilbert space is D2, then the dimension of the tensor product is D1 times D2. So this has drastic consequences if we scale up the system now. So suppose that that Hj, so our composite, our individual systems, are two-level systems. Okay, and our composite system, so the total system, is built of this two-level system. Say it's H1 to Hn. Then this is nothing else but C2 to the tensor power n. Then the dimension of this composite system is the dimension of C squared tensor power n, which is 2 to the n. Okay, so it scales exponentially with the number of two-level systems. And that's why many-body quantum systems are so hard to simulate. Okay, because once you increase the size, then the Hilbert space increases exponentially. Simply think of a system of 10 qubits, then we have the Hilbert space dimension 2 to the power of 10. Okay, it's a huge number. If you really want to simulate this in a classical computer, then your density operators are 2 to the power of 10 times 2 to the power of 10 matrices with which you have to perform the simulation. That's why many-body quantum systems are so hard to deal with. Okay, then the second remark. Okay, the elements of our composite system are the tensor products. Are tensor products V tensor W with V in H1 and W in H2, but I think this is clear. But more interesting is our third remark, namely if Vj, so the set Vj is no n basis, of H1, and Wj, or say now Wk, is an orthonormal basis of H2, then the set Vj times Wk running over the indices j and k is an ON basis of H1 tensor H2. So meaning that once we find ON basis of each individual system, by combining them via the tensor products, we have an ON basis of the composite system. And then number 4. Okay, number 4 is about notation. So we write this tensor product V tensor W most of the time simply as VW or as VW or like this. So it's simply shorthand notations that we're going to use often. Now about operators. Okay, there's an interesting decomposition of operators. So an arbitrary operator, so it's a linear operator. Okay. I hope this is clear. An arbitrary operator C on H1 tensor H2 can be written as C is the sum over J with some coefficients Aj, and then operators Aj tensor Bj. It's equation 139. With Aj in C, and this, the capital H's are operators on H1, and the Bj's are operators on H2. So we can always write such an operator in such a decomposition. You can find these operators and coefficients such that you can bring it in this form. And then if you multiply this with a vector V tensor W, you get so it's again component-wise. These operators act always on the respective states of their Hilbert space in a component-wise fashion. And our last remark is given an ON basis Vj of H1 and Wk of H2, then we can express okay, then arbitrary operator A on H1 tensor H2 can be written as, okay, I'm going to write it down here. There's enough space. So it can be written as A is equal to sum over J, J prime, K, K prime. Then the coefficients A, J, J prime, K, K prime, and then we have V, J, V, J prime, O times W, J, W, J prime. So this is nothing else but the outer product representation of an operator on this composite system, right? And if you remember, if we have only a single, if you only consider a single partite system, then this one here vanishes, and we only have here the coefficients j, right? Now we enlarge this to a composite system with two parties. Then we also have to sum over the basis states of our second component. So this enlarges and we get some more coefficients. And these coefficients are nothing else than the matrix representation of our operator with respect to the spaces V and W. And matrix representations of composite systems is exactly what we're going to do after the break. So at this point, let us do a break and meet in 10 minutes. Let us continue now with describing composite systems. In particular, I'd now like to discuss the matrix representation. So this is chapter 1.4.2. So the matrix representation of a tensor product is simply given by the so-called Kronecker product of their matrix representations. So the matrix representation of the tensor product A tensor B of A in H1, A lives on H1 and B on H2 is given by the Kronecker product of the matrix representation of the matrix representations of A and B. So this means that the representation of A tensor B is something like A11 times the matrix B, okay, to A, say, okay, the dimensionality is D1, so we have A D1 1B, and this goes to A1 D1B to A D1 D1B. So what is this? This is a scalar times a matrix. Okay. So A JK B is A JK B11 to A JK B D21, and here we go to A JK B1 D2 to A JK B D2 D2. So hence A tensor B, so the matrix representation of H tensor B is a D1 times D2 times D1 D2 matrix. Then the Kronecker product for state vectors. We now call them simply for vectors. It works similar. So for say psi 1 to psi d1 and phi is phi 1 to phi d2. The Kronecker product is as follows. So we have psi o times phi is equal to psi1, and here then the vector phi1 to phi d2, and this continues to psi n of, and then multiplied with phi1 to phi d2. Sorry, this is d1. And it's nothing else but, okay, psi1, phi1 is the first entry, and then we have psi1, phi2, and so on to psi1, phi d2, and then we psi2, phi1, and so on to psi d1, phi1 to psi d1, phi d2. This is equation 1.44. And to get a bit more familiar, let us do an example. So let's take the state psi is equal to 1 over square root of 5, 1, 2. So this is a normalized vector. And phi is equal to 1 over 5, 3, 4. It's also a normalized vector. Then we have psi. Kronecker product of phi and psi is 1 over 5 times square root of 5. Then we have 1 times this vector 3, 4, and 2 times the vector 3, 4, which is 1 over 5 square root of 5, 3, 4, 6, 8. So please be aware that we denote the Kronecker product and the tensor product with these O times. Okay? So here it's the Kronecker product, because what we do is we do the Kronecker product between these two matrix representations. But if we're on this formal Hilbert space, then, and we have some state vectors, then this O times denotes the tensor product, right? So the Kronecker product is how we calculate the tensor product on the level of our matrix representation. And both are denoted by this O times. So we have now set up the formalism that we can consider bipartite systems or even multipartite systems, right? But often it's the case that you have a system which is, for example, bipartite or has more parties, but you only have access to one of these systems. And you cannot, for example, measure the other system. Okay? For example, if Alice and Bob share a state and you are Bob, so you can only perform a measurement of this composite state in your system. So what this means is you'd like to describe now the state of your system, okay, without the state of Alice, of Bob's system, if you are Alice. Right? Meaning that you want to exclude all the degrees of freedom of the other system because you do not have access to these degrees of freedom. This, for example, happens if you have a quantum state which is connected to some environment. Then you usually cannot measure the environment. Possibly it has a lot of degrees of freedom, so you usually cannot measure the environment, but you can measure your system, and you can, in order to describe the measurements of the system, what you have to do is you have to get rid of this environment in your formalism, and this formally, how you do it is you trace out this system that you do not have access to. So you want to describe your system by the so-called reduced density operator. Okay. So this brings us now to the next subsection, which is the so-called partial trace. So suppose we have a bipartite state rho AB, which is a density operator on the composite state rho A tensor rho B. And we want to describe, so and we have no access to subsystem B. Hence, we want to describe the reduced density operator rho A of system A alone. So this we can do by the so-called partial trace. So this is obtained by this is obtained from rho AB by performing the partial trace over the subsystem B. So we usually write this that our reduced density operator of system A is given by the partial trace over system B of our composite state rho AB. So now you might wonder, how do we calculate this? So this is defined as follows. The partial trace is defined to be linear, so it is linear in its inputs and defined as trace over B of V1 V2 tensor W1 W2 is a trace of W1 W2 and then with V1 V2, which is W2 W1 and then V1 V2. So the partial trace over system B is given by simply tracing only in this subspace from system B. So we trace only on the subspace and leave the subspace of system A alone, right? And then performing the trace gives this expression, and the subsystem A is left alone. And with this we can trace out the subsystem B. Then the definition is not obvious. But the reason why it's defined like this, they're going to write it down in a second. So the reason why we define it like this is because it gives the right measurement statistics. Okay, so remarks. This definition gives the right measurement statistics. Well, by this I mean that if we have such a composite system and if we trace out subsystem B and perform a measurement on subsystem A, then we get the right measurement statistics as we would expect it. And being more precise, so more precisely, so for more precisely for any, or how should I say it? Okay, more precisely, the partial trace is the unique, so it's unique, the unique function such that for all linear operators M, that the trace of M times rho A is equal to the trace of M tensor the identity of rho AB. Okay, this is formally expressed that by this definition of the partial trace, we get the right measurement statistics. Because what this here says, okay, you know this expression from the measurement. So we have some measurement operators in our state, right? And this gives the statistics, meaning that the probabilities. So this is the same expression as for the probabilities of a quantum measurement, right? And this is for the subsystem A alone. And here on the right-hand side, this is the very same thing if we would perform a measurement which does actually nothing on our subsystem B, but the measurement M on our subsystem A of our composite system, right? And going from this row AB to row A, this is done via the partial trace. And the definition of the partial trace is such that this equality holds for all linear operators M. So this is the reason why this definition of the partial trace is the right definition in order to get the measurement statistics correctly. So let's do an example. First, suppose that we have an uncorrelated state. So suppose we have rho AB is equal to rho 1, or say to rho tensor sigma. Okay, so it's uncorrelated, since we write this as a tensor product. If you remember our postulate 4 of the composite quantum systems, there we stated that if we prepare the systems separately, then we can express this as such tensor products. So meaning this state is nothing else than a separate preparation of system A and system B. Okay? So what we would expect if we trace out system B, that we get simply rho. So let's do this. So let's perform our, let's say, okay, let's calculate the reduced density operator of system A, which is the trace over subsystem B of rho AB, which is the trace over B from rho tensor sigma, which is the trace of sigma and then times rho. Okay? And then we know that the trace of a density operator is 1, so we get out rho as expected. But the whole thing changes if we do have correlations between those subsystems. And to this end, let us also consider an example. Let us suppose now that rho AB is given by this pure state psi, where psi is this state here, 0, 0, plus 1, 1. And now let me trace out the subsystem B. So let me calculate now explicitly our reduced density operator of system A. So we have rho A is equal to trace over B of rho AB equal to trace over B. So this is 1/2, and then we have 0, 0, plus 1, 1, and here 0, 0, plus 1, 1. Which is 1/2 trace B of 1/2, and then we have multiplying this out, it gives 0, 0, 0, 0, plus 0, 0, 1, 1, plus 1, 1, 0, 0, plus 1, 1, 1, 1. Okay, now we perform the trace over the subsystem B. So the subsystem B is, I'm going to mark this in red, it's this one. So we trace out over the second components. This gives 1/2, and the first thing gives 0, 0. So this is the trace, and then the first system remains here in this. Then we have 1, 0, 0, 1, plus 0, 1, 1, 0, plus 1, 1, 1, 1. Okay, now we see this inner product is 1, this is 0, this is 0, and this is 1. So this equals 1, equals 0, equals 0, equals 1. And we are left with 1/2, 0, 0, plus 1, 1, which is 1/2 the identity matrix. So what we see is that our reduced state of subsystem A is maximally mixed. So hence rho A is maximally mixed, since trace of rho A squared is equal to 1/2 is equal to 1 over the dimension of the subsystem HA. So I think I didn't explicitly state that if HA is the two-level system and B is also the two-level system. So if you remember, we did define this expression here as the purity And if this gives 1 over the dimension, then this is the lower bound of the purity, and then we call such a state maximally mixed. So with this we get a maximally mixed state. But further observe the following. So first, that the joint state of the system is pure, and hence it is perfectly known. Okay? The joint state psi is pure, and hence it's perfectly known, while the reduced state rho A is maximally mixed, and hence it's completely undetermined. So what do I mean by completely undetermined? So if you perform a measurement now, say you do have the subsystem A under control, and you perform a measurement in the subsystem A. Suppose a measurement, so suppose you perform the measurement with measurement operators the project onto the 0 and project onto the 1 subspace. So if you measure this state here with this projective measurement, you will get with 50% 0 and 50% 1. So the outcome is completely undetermined. Well, and if you perform an orthonormal measurement in another basis, then the outcome is also completely undetermined, okay? Because here we have the identity matrix. So no matter in which basis I measure, I will always get a random outcome. Okay? On the other hand, if in system A in this basis, and subsequently I measure system B, also in this basis, I get a perfect correlation between the outcome of system A and system B. Okay? The reason is that this state psi is a pure state as a composite system, and the reason that I get a perfect correlation then is due to the state's entanglement. So let's finish this first. So if you measure, if you subsequently So and this, the fact that they have these perfect correlations is independent on the basis in which you measure. So I now say that this is a manifestation of the state's entanglement. So let's, before we now define entanglement, let me say this again. So we have a combined state of system A and B, which is pure, so it's perfectly known. And if we now trace out subsystem B, we get the maximally mixed state. And this gives us a random outcome if we perform a measurement with measurement operators in an orthonormal basis. And this randomness holds for any basis that we choose, right? However, if we now, after our measurement of system A, measure system B, then the outcome of system B is perfectly correlated with the outcome of subsystem A, even though for subsystem A, these outcomes are really random. And this can only be due to a correlation between the state of system A and B together. And this correlation is called entanglement. And entanglement is what we're going to study in more detail at the end of the lecture. So there I'd like to give you an introduction into entanglement theory. And here we simply now restrict to bipartite pure states entanglement. In particular, I only give a definition under which condition a bipartite pure state is entangled. Okay? And entanglement theory is then what we're going to discuss, hopefully, at the end of the lecture in more detail. So with chapter 1.4.4, so this is a definition, 1.17. A bipartite pure state psi in HA tensor HB is called entangled. If it cannot be written as psi A tensor psi B for any psi A in HA and psi B in HB. So this is what we call a product state, right? And then we here defined entanglement such that if we cannot write the state as a product state, then we call it entangled. So note that this only holds for bipartite pure states. Okay, once we consider mixed states, then entanglement or defining entanglement is much more involving. Okay, that's why for the moment I only restrict here to bipartite pure states. Let me now finish with some examples. So the first example, or our examples, say the composite Hilbert space is given by the tensor product of two level systems. And now, okay, consider the state. So consider this state 0, 0, minus 0, 1, plus 1, 0, minus 1, 1. Okay, is it entangled or not? Right, we can write this as 1 over square root of 2, O plus 1, and then O times 1 over square root of 2, 0 minus 1. So if you multiply this out, you get this. And hence we see we can write this as a product state. So this is the plus state and this is the minus state. So we can conclude that psi is not entangled. Then another example is actually what we discussed in order to motivate the discussion of entanglement was this state. So consider this state. So this state here is indeed entangled, and you cannot find any states such that you can write it as a product state here. So it's not possible to write this as psi A O times psi B. That's why the state is entangled. So indeed, this is one of the so-called Bell states. So this is the usual convention of the Bell states. Which is in equation 1.50. So the Bell states are maximally entangled states. On this Hilbert space. So what it means that a state is maximally entangled, this we're going to discuss at the end of the lecture when we dive into entanglement theory. Okay? So from here you can, I think it's enough to state that you cannot, or say this a maximally entangled state has maximal quantum correlations. Okay? But what this means will be discussed at the end. So this is the usual convention of the Bell states, and in the exercises you will show that these Bell states form a also normal basis of this Hilbert space of two-level systems. And with this I'd like to finish here. So see you next time, Wednesday.